Hello APC Mechanics students, today we will solve the past paper of RQ 2017, exercise 1. An Atwood's machine consists of two blocks connected by a light string that passes over a frictionless pulley of negligible mass. Then the pulley is ideal, which means any argumentations that we've studied throughout the course can be used here. As shown in the figure above, the masses of the two blocks M1 and M2 can be varied. M2 is always greater than M1. When M2 is always greater than M1, so this will accelerate down and that would accelerate up. Part A, on the dots below, which represents the blocks, draw and label the forces, not components, that act on the blocks. Each force must be represented by a distinct arrow starting on and pointing away from the appropriate dot. The relative lengths of the arrows should show relative magnitudes of the forces. So basically they're giving me instructions on the FBDs. Now, what are the forces acting on the block M1? We have the pull of gravity down, tension up, but we should be careful to show the relative magnitudes of the forces. Because it's accelerating up, then the tension force would be greater than the pull of gravity. Also, before you represent the forces, take into consideration the space of the grids that you have. So here I will represent the pull of gravity as one grid and the tension to be two grids up. I will explain why. Always use a ruler. That would be the force given by M1G, and that would be the force given by the tension. Now tension here would be equal to tension here because the pulley is massless and tension is transmitted equally across all ends of the rope, left and right, so this is perfectly up. And in this case, the pull of gravity, which is for M2, will be represented by 3 grids down to indicate that M2G is greater than the tension. So this is it for part A. Now in part B, using the forces in your diagrams above, write an equation applying Newton's second law to each block and use these two equations to derive the magnitude of the acceleration of the blocks and show that it is given by the equation given by fractional mass multiplied by g. Remember from the course the architecture. In order to solve for the acceleration for the system, we need to utilize Newton's second law for the first FBD, second FBD, get the tension from each one, equate them, and solve for the acceleration. So basically that's what we will be doing here. Let me start by applying Newton's second law to M1. Now what are the forces? So let me write Newton's second law given by F naught is M1A. So let me keep this as a general mass. Now what are the forces acting on block 1? We have the tension T, we have M1G. Now here the vector, whether it's represented above G or above M1G, it's the same, and that would be mass M1A. Now up is positive. Now remember, this is a vector equation that gives the birth of two linear equations. We're only interested in the vertical direction. Up is positive, then this is T minus M1G is M1A. Remember that A in this case has no projection because already up is positive. Then the tension is given by M1A plus M1G. Now we need to get the tension from the second FBD. So apply Newton's second law to M2, and that would be F naught is MA. What are the forces acting on 2? That would be the tension plus M2G is M2A. Now this is a vector equation that gives the birth of two linear equations. We are only interested in the vertical. Let's take down is positive. Then that would be minus T plus M2G is M2A and solving for the tension, dragging this to the right hand side and this to the left hand side, we would have that the tension is M2G minus M2A. These two tensions are equal due to the assumptions given in the exercise. Tension equals to the tension, that would be M1A plus M1G equals M2G minus M2A, and we're solving for the acceleration. So what's the type of this equation? This is a linear equation. We drag this to the left and this to the right, factoring the acceleration. That would be M1 plus M2 equals to M2 minus M1 multiplied by G. Then the acceleration indeed is given by fractional mass, M2 minus M1 divided by M2 plus M1 multiplied by G. And whenever you arrive this expression, make sure that you compare it with the given expression as well, which is given by M2 minus M1 over M2 plus M1 indeed multiplied by G. Now the magnitude of the acceleration A was measured for different values of M1 and M2, and the data are shown below. So we have a table that consists of 3 rows and 6 columns. We have the values of M1, M2 and the corresponding acceleration for each mass configuration. Indicate below which quantities should be graphed to yield a straight line whose slope could be used to calculate a numerical value for the acceleration due to gravity G. So now we know that the acceleration is given by M2 minus M1 divided by M2 plus M1, so multiplied by G. We are interested in graphing this equality such that the curve would be a straight line whose slope is given by the gravitational acceleration. So let me write here this G to be the slope in the middle, and we have acceleration, so M2 minus M1 over M2 plus M1. So in order for this to be in agreement with a straight line which is given by y is equal to ax plus b, so b in this case is set to be 0. Now on the y-axis we would represent the acceleration, the slope would be g, and in this case on the x-axis we should graph the fractional mass. Alright, this is not part of the answer, then let me erase it. Then on the vertical axis we will plot the acceleration, and on the horizontal axis we will plot the fractional mass given by M2 minus M1 divided by M2 plus M1. Use the remaining rows in the table above as needed to record any quantities that you indicated that aren't given. So basically always you expect that they will give you additional empty spaces or rows, just not to link the solution in what is given. Okay, so basically we have the acceleration. Now we need to complete this row by recording here M2 minus M1 divided by M2 plus M1. Then we have the values of M1, M2. We can determine the fractional mass. I will do, so they're telling you to record, so we need to record also the values, not only the expression. So I will only do it for the first one, then completed them directly for all the others. For the first one, so M2 is given by 2 minus 1 divided by 2 plus 1, that would be 1 over 3, which is basically 0.33. And notice that here all quantities in physics have unit. Here we didn't include the unit because simply they are included in the first column. So if you do the calculation, that would be 0.33, that would be 0.20, that would be 0.41, and that would be 0.14, and that would be 0.17, and I'm representing my numbers as 3 significant figures. Now plot the data points for the quantities indicated in part C on the graph below. Clearly scale and label all axes including units. If appropriate, draw a straight line that best represents the data. So let me draw the x-axis, and let me draw the y-axis. So on the x-axis we agreed to plot the fractional mass given by m2 minus m1 divided by m2 plus m1. Now we need to include the unit. Remember that the fractional mass here I didn't include a unit. Why? Because kg minus kg over kg plus kg, that would give you kg divided by kg, which is basically 1, so no unit. For this reason here I didn't represent a unit, and here I won't represent unit as well. Before now, we start always from the origin. Before I split the axes, we need to take a look about the values that we have. The values of the fractional mass basically ranges from 0.1 up to 0.4. Then let's divide it by a step of 0.1. So this is 0.1, 0.2, 0.3, 0.4, and that would be perfectly 0.5. On the vertical axis, as we have agreed, we're gonna plot the acceleration and the unit of the acceleration, because they're telling me clearly scale and label all axes including units. That would be meter per second square if appropriate. So for this reason this doesn't have a unit. Acceleration ranges basically from 1 up to 4. So let's split this axis by unit by step of 1. And now we're ready to plot our data. The first fractional mass is given by 0.33. So that would be, if you notice here carefully, this is 0.32, 0.34, 36, 38, 40. We're interested in 0.33, which is somewhere here. So I will erase this later. Now with an acceleration given by 3. So the acceleration would be somewhere here. So this is our first point. Let me represent it by a bold dot. And let me erase this. The second point would correspond for a fractional mass given by 0.2, which is basically here, and for an acceleration given by 1.82. So its corresponding point, also the y-axis or the a-axis would be 1.2, 1.4, 1.6, 1.8. Then that would be perfectly here. Now for the third point is given by 0.41 and with an acceleration 4.21. So 0.41 with an acceleration 4.21. So it would be perfectly somewhere here. Okay. Now for this point 0.14, which is here, with an acceleration of 1.15, so it would be here. Okay, so 0.14, sorry, 0.14, the acceleration is given by 1.15. So this is 1.2, and that would be 1.15, sorry, that would be 1.2. 1.15 would be midway. Then let me erase this. And we still have a point which is basically 0.17, that is 1618 here, with a value of acceleration given by 1.71, 2468. Then that would be here, 68. Okay. And now let's draw our best fit line. And remember that in the best fit line, the line must passes through most of the points or should be equidistant if it's not passing through the points. So let me try to make it so. So basically that would be good. Now notice that when I'm trying to draw the line, I'm trying to draw it in a way to pass through perfect points in order for the slope calculation to be easy. So basically I'm aiming for this point. So I have aimed for this point, which looks perfect, and I have aimed also for this point, let me say, which also looks neat. Okay, so this is our drawing for the best fit line. Now in part E we need to determine an experimental value of G, and this is determined from the slope. So let me say that G equals the slope. But before we determine the slope, we need to choose our points. Let me say this is the point A. Now remember, we need to choose the points that are not recorded from the experiment itself, but recorded from the best fit line. So I will avoid this point, this point, this point, this point, this point. The points should lie on the best fit line. So my choice would be with A. I will represent it by an X, just to distinguish it from other points. The coordinates of this point A is given by 2, 4, 6, so 1.6 with no unit, and with 1.4, and the unit along the vertical is meter per second square. Now B is this choice given by 0.42 with no unit, and its vertical would be given by 4.2 meter per second square. So in this case, what do we have? We have 4.2 minus 1.4, and the unit is given by meter per second square, and the denominator is given by 0. So I think 1.6 is wrong, because this should be 0.16, so let me correct it. So that would be 0.42 minus 0.16, and plugging this fraction on the calculator, we would have a value of 10.76 meter per second square. Remember that this is an experimental value of a G, so we expect, so there is no correct or wrong answer. The important thing that we're doing our steps carefully, and we know that the value of G is given up to 9.8 or 10. So taking into consideration the experimental error, this is an accepted answer. But for example, if it's 11.5 at 12, this means it's exceeding the experimental error. So this is it for part E. Now on the next page, the experiment now is repeated with a modification. So this is a modified Atwood machine. The Atwood's machine is now set up so that the block of mass M1 on a smooth horizontal table, and the block of mass 2 is hanging over the side of the table, as shown in the figure. Smooth means that here we have no friction, and still we're using the same pulley, which is ideal. For the same values of M1, M2, is the magnitude of the tension in the string when the blocks are moving higher, lower, or equal to the magnitude of the tension in the string when the blocks are moving in the first experiment. So we need to compare the tension in this string to the tension in the previous string for the previous modification. So what will differ from this modification to the previous modification is the expression of the acceleration. So let's start our argumentation by referring to the acceleration, and let me say the acceleration of the system. What happens to the acceleration of the system? Previously, the acceleration is given by m2 minus m1 divided by m2 plus m1 multiplied by g. Now we know for this modification, m1 will vanish, and the fractional mass is given by m2 over m2 plus m1 multiplied by g, which means that the numerator will increase, then the acceleration will increase. But remember that this is not part of the answer, then let me erase it. So I will claim that the acceleration of the system increases from A is given by m2 minus m1 divided by m2 plus m1 multiplied by G to a value given by A is M2 over M2 plus M1 multiplied by G. And now what happens if the acceleration increases? So basically the acceleration increases, and the acceleration in this case is expressed as what? So we have the pull of gravity down minus the tension is equal to M2A. So basically the acceleration is coming due to forces, the pull of gravity and the tension. But the pull of gravity didn't increase because we didn't change M2G, which means that the tension has been reduced in order for the acceleration to increase. For this reason, we will say, but M2G remains the same, which means the tension in the string decreases compared to the previous experiment. Now in part A, they're telling you the value determined for the acceleration due to gravity G is lower than in the first experiment. Give one physical factor that could account for this lower value and explain how this factor affected the experiment. Now in the previous experiment, the blocks were hanging vertically. Now in this experiment, one of them is being sliding on a table and the other is vertical. So what's the difference between the first and the second is the introduction or introducing this table. And they're telling you, give one physical factor that could account for a lower value of G, and this might happen due to the friction between M1 and the table. Although we're assuming that it's smooth, which means friction is negligible, however still we have friction. So the physical factor that might affect our calculation is friction. So friction is the physical factor. I repeat, although they said it's smooth, but which means friction is negligible, however friction still exists. In the presence of friction, so why friction affects the value of G? Because friction as a force, it will enter into the game in Newton's second law, so that would affect the acceleration. Then the acceleration would decrease. Then what happens to the slope? They're claiming in the exercise then the slope is lower. So let me say then the slope of the line decreases. This will affect the value of G calculated in experiment 2. And let me mention between brackets lower value. Then that's it for me in this video, guys. See you soon in a new one.